you might have learned that SN1 reactions can result in two products, one having the same configuration as that of the reactant and the other with an inverted configuration. However, SN2 reactions gives only inverted product. Can you explain this? This video deals with the stereochemical aspects of organic reactions. To understand this, we will start our discussion with optical activity. When ordinary light is passed through a polarizer, it produces a light which rotates only in one direction. This light is called plane polarized light. When plane polarized light is passed through solutions of certain compounds, they rotate the plane polarized light in a specific direction. Such compounds are called optically active compounds, and the phenomenon is called optical activity. The angle by which the plane polarized light rotated by an optically active compound is measured by an instrument called polarimeter. If the optically active compound rotates the plane polarized light to the right or the clockwise direction as seen by an observer towards whom the light is approaching, then the compound is called dextrorotatory or the D form of the compound. On the other hand, if the optically active compound rotates the plane polarized light to the left or the counterclockwise direction, then it is called levorotatory or L form. For example, lactic acid rotates the plane polarized light to the right and is called D or plus lactic acid. The D form is indicated by placing a positive sign before the degree of rotation and L form by a negative sign. Such positive and negative isomers of a compound are called optical isomers, and this phenomenon is termed optical isomerism. It was observed that solutions of two crystalline forms of same compound can show optical rotation, which is equal in magnitude but opposite in direction. Louis Pasteur suggested that this optical activity is related to the three-dimensional arrangements or configurations of atoms in molecules. Van Hoff and Label independently suggested that if all the substituents attached to that carbon are different, then such carbon atoms are called asymmetric carbon or stereocenter. The resulting molecules are referred to as asymmetric molecules. This asymmetry can result in optical activity. Such molecules are not superimposable on their mirror images. They are called chiral molecules, and this property is called chirality. Chiral molecules are optically active. Now consider 2-propanol. Here the substituents on tetrahedral carbon are not different. Therefore, 2-propanol is not asymmetric, or you may say it is achiral. Achiral molecules are not expected to be optically active. In fact, chiral molecules may contain one or more stereocenters. For example, tartaric acid contains two stereoisomers. Such stereoisomers related to each other as non-superimposable mirror images are called enantiomers. Enantiomers have identical physical properties such as melting point, boiling point, solubility, refractive index, etc. However, they differ in the way in which the plane polarized light is rotated. If one of the enantiomers is dextrorotatory, the other will be levorotatory. If a solution contains two enantiomers in equal proportions, then that solution shows zero optical rotation. Here, the rotation due to one isomer is cancelled by the rotation due to the other isomer. Such a mixture is called a racemic mixture. The process of conversion of an enantiomer into a racemic mixture is known as racemization. If the spatial arrangement of bonds to an asymmetric center is retained during a chemical reaction, then it is called the retention of configuration. Here, no bond to the stereocenter is broken. The product will have the same configuration of groups around the stereocenter as that of the reactant. If the chemical reaction results in a product whose configuration is opposite to that of the reactant, then it is called inversion of configuration. If a 1:1 mixture of inversion and retention is obtained, then the process is called racemization and the product is optically inactive. In the case of optically active alkyl halides, say for example -2-bromobutane, the hydrolysis of 2-bromobutane by SN1 mechanism is accompanied by racemization. Here the intermediate carbocation is achiral. The nucleophile OH- can attack from the top or the bottom of the plane containing the carbocation. The attack of OH- from the side opposite to that of the leaving group gives the inverted product. The attack of OH- on planar carbocation from the same side as that of the leaving group gives the retention product. Thus, a mixture of products plus or minus butane 2-ol are formed, leading to the racemic mixture. On the other hand, SN2 reactions of optically active halides are accompanied by complete inversion of configuration. The reaction of -2 bromooctane with sodium hydroxide to form +2 octanol is an example. This reaction occurs in a single step. Here the nucleophile OH- attacks from the backside of the leaving group. Thus the OH group occupies the position opposite to that of the bromide which had occupied, resulting in an inverted product. Now, as we come to the end of the session, can you predict the optical activity of the following structure? With this, we will summarize this video.
Manorama Horizon. Learning made simple.